Chapter 12, Deflection of Beams and Shafts. Example number 10, Solution 3. If you remember from previous sections, we have solved this problem with two previous approach. So we have a 1 degree indeterminate structure. A beam, one side is a fixed support and the other is a ball support. So there is a 1 degree of indeterminacy and handling a uniformly distributed load of W, and we want to know what reaction at A is, what reaction at B is, and what is the angle at B, because at A we don't have any. So this time we can consider the reaction at B as a result as a redundant a force. So just assume that we consider reaction at B as a redundant. Mhm. And then convert the original beam to a cantilever beam with the uniformly distributed load of W plus a cantilever beam just handling the reaction RB. Mhm. So we apply RB as a unknown to the structure, see the effect, and then calculate the reaction at B. Mhm. So again, in this solution, if you the key to solving the problem is that tangential deviation of B with respect to A for the original beam is 0. So if you draw a line from A tangent to the deflection at A and you observe the vertical distance at B, that's 0. So that's TB over A, or T uh, of B with respect to A equal to 0. And if you if you divide your main original beam to these two beams, that says for the cantilever beam with uniformly distributed load of W, we have a tangential deviation of TB over A TB with respect to A due to weight, and the other one is a upward movement of TB with respect to A resulted from a reaction at B, unknown force of RB at B. So if you add them up together, so to get the uh, tangential deviation, we need the moment area method. So if you draw the moment over area diagram for a uniformly distributed load, that's TB with respect to A is area under M over EI. So that's a TB over A is a moment area under moment over EI from A to B times X, and X is the centroid measured from centroid to B. So we need to calculate this area, which if that's a constant, that's a linear, and moment over EI is a second degree. So if that's second degree, the area under that is 1/3 of WL squared over 2EI times 2/3 of L. Mhm. And that's a, let me modify this, that's a 3/4. Mhm. So that cancels out with these 3 at denominator, and that's a 4 times 2 goes by 8. So the distance for a second degree is a 1/4 from the base and 3/4 from the other end. So that's a 1 third of WL squared over 2a times 3 quarter of, and that gives you WL to the fourth over 8 EI. And at the same time, tangential TB, which is theta b with respect to a, and theta at a is 0. So theta b is area under m over EI. So that's a WL cubed over 6 EI. Hmm? And that's for the first part. And for the other part, it's a TB with respect to A for due to reaction at B. So if you do so, it just gives you a TB over A due to reaction at B. It gives you 1 over 3 EI RBL cubed. And theta at B for second condition, which is this part, is a just area under M over EI. And that's a half of RB times L over EI times L. So that's height times length. Mhm. So again, in this case, TB over A total is the summation of these two. We have calculate both of them separately. Now we add them up together. We get so total TB over A is the first part plus second part. Add them up together, and we have the first part, which is a negative area, a negative WL to the fourth over 8 EI, plus a positive area, which RB is unknown, and that should go 0 due to the fact that we already know it from the geometry. So that gives us RB, reaction at B is 3 over 8 times WL. As soon as you know the first reaction, you can easily calculate the second one, which is 5 over 8 WL. And if you want to know the theta at B, it's just a summation of area under M over EI for the two diagram. So the theta for part A is WL cubed over 6, and that's a negative, as you can see here. And the other one is a positive 3 over 16 EI WL cubed. That's EI. Mhm. And if you add them up together, it just says theta total is theta at B is a 1 over 48 EI WL cubed. Mhm. And at the same time, when we know RB is 3 over 8 WL, the other just is 5 over 8 WL to cancel out WL. The total is goes by 8 over 8 WL, and at the same time we calculate the theta at B, which is WL cubed over 48 EI, which is the same parametric value which we calculate in conventional with integration method, both when we consider moment at A is a redundant, and also as well as RB. In next video, we'll solve it in a Castigliano's method, which is the far simpler than the previous methods. Thank you.